Hi, I'm Leslie. Thank you so much for joining us this afternoon so we can talk about how to run the SCREEN3 model. So I've been doing air dispersion modeling for a very long time. I've been in environmental consulting for almost 20 years and have had the good fortune to work on air modeling projects for lots of different types of industries. I also work with our software group here at Providence. We sell air dispersion modeling software and provide training on how to use air quality models. So this presentation is going to be mostly kind of a mechanical walkthrough of how to run the SCREEN3 model, how to collect all your inputs, how to run the model, how to view your outputs. But before we get started, I want to throw out just a couple of terms that I might be saying over the course of the presentation. One is just the term ORIS or Providence ORIS. If I say that, I'm simply referring to the software team at Providence. Also, SCREEN3 is a single source model, and that is exactly what it sounds like. It's a model that can accommodate only one source of emissions. So if you have a project where you have a whole refinery full of sources that you need to model, SCREEN3 is probably not the best choice. It's best for one model. And if you need to do more than one source, you'll have to run SCREEN3 a few different times. SCREEN3 is also a Gaussian plume model, and that just means that the dispersion algorithm in SCREEN3 will disperse the plume along this Gaussian bell curve. So it means that the pollutants are going to be more concentrated toward the center of the plume, more concentrated toward the source itself, and then it'll start to dissipate as you go along the edges of this bell curve. Okay, if you are interested in downloading or in running SCREEN3, the first thing you have to do is download it. And you have two choices here. One is you can download it directly from EPA, from the SCRAM website, and that'll be the out-of-the-box DOS version of SCREEN3. Or you have the option of downloading it from us, from the Providence ORIS website. Our version of SCREEN3 is also free, and it's all our version is really is a graphical user interface that overlays the EPA version of SCREEN3. So when you run it, you get exactly the same results as you do with the EPA version. It's just a little bit easier to collect your inputs and view your outputs with the Providence version. So for the purposes of this presentation, I'm going to go ahead and use the Providence SCREEN3 for Windows. Okay, so the vast majority of the time that you're going to spend putting together a SCREEN3 run is going to be collecting the inputs, deciding what input you need and collecting that information to put into SCREEN3. We're going to talk about the different source types that you'll have to decide between, and some of the other input data, the rural and urban option, meteorology selections, terrain options, receptor options, and building downwash. And one thing I haven't noted in the rest of this presentation is if you want to run SCREEN3, you also have to have an emission rate. If there's no emission rate, the model will not run, unfortunately. Okay, if you're going to run SCREEN3, you have to choose between one of these four types of sources: a point source, a flare, an area source, or a volume source. What's a point source? Point sources are traditional stacks with a dedicated vent. I have some pictures here of some typical point sources. This is just a little generator set with a short stubby stack on the top, and we have a really big industrial boiler here. This is a tiny like medical waste incinerator on this side. This is a cat cracker at a chemical plant. It's got a whole bunch of stacks over here. And then this looks like a power plant to me on this side, but it's pretty easy to see. It has like a typical kind of smokestack design. So if you're going to model a point source, you'll need the stack height, you'll need the stack diameter, you will need the exit velocity. And when I say exit velocity for the exhaust, I mean exit velocity in an upward direction. If your stack is actually knocked over, so it's venting horizontally or at an angle or something, we're going to have to adjust that velocity. So we're only looking at the amount of the velocity that actually goes upward. You also have the option of using the volumetric flow rate if you don't have the velocity handy. And then you also need the temperature of the exhaust. Flares. So flares are in their own source category in SCREEN3. Some pretty flare pictures down here. But flares are just sources where excess combustible gases are burned. If you're going to model a flare in SCREEN3, you'll need the flare tip height above the ground, and you'll need the heat release, which is a value in units of either BTUs per hour or calories per second. It'll be just a combination of the heat content of the material sent to the flare and the flow rate of the gas that's sent to the flare. And then SCREEN3 will automatically assign a couple of other values, an exit velocity and a temperature, but that'll be internal to the model, so you won't need to mess with that at all. Quick note about flares. Flares are some sources that burn excess gas. Vapor combustors and incinerators sometimes do the same thing, but vapor combustors and incinerators are not flares, not in terms of the source type anyway. So that's a separate thing. Area sources. So an area source is a source with a fugitive emission rate that's released over a flat two-dimensional area. These are some examples of area sources. You might have an evaporative cooling pond or a clarifier tank, anything where your emissions are spread out over a flat area. So in order to model an area source, you'll just need three pieces of information. You'll need the release height above the ground. You'll need the length of the area and the width of the area. And so SCREEN3 automatically assumes that your area is a rectangle and it has a specific length and a specific width. Now, it's possible that your area isn't a rectangle at all. It could be circular, it could be a weird shaped polygon or something. If you have an area source that is not a rectangle, you have to figure out the area of whatever your area source is, and then back out a length and a width for a rectangle that has the same area. That'll be like an effective square or an effective rectangle with the same area. And then you'll have a length and a width that you can use to put into SCREEN3. Volume sources, a little bit more complicated. Like area sources, they're good for fugitive emissions, but they're best for sets of fugitive emissions that are initially released over a three-dimensional area, not just a flat area. Volume sources are great for, I didn't find a good picture, but if you have a building like a workshop with a bunch of open windows and doors where little bits of emissions kind of leak out from all over the place, that's a good volume source. Also, you can use it for collections of piping and equipment, kind of fugitives. You can use it for material drop points, and you can use it for loading. But again, it's for any kind of non-buoyant fugitive release over a three-dimensional area. If you want to model a volume source, you need three pieces of information. You'll need the release height, you'll need the initial horizontal dimension, or sigma y, and the initial vertical dimension, sigma z. Well, I don't know what that is. When you decide you're going to model a volume source, you have to kind of imagine a box, like just a rectangular box around your source. And once you know what the dimensions of that box are, you use this table, which is in the SCREEN3 user's guide, to help you calculate what those sigma y and sigma z values. So you'll see that in SCREEN3, all of the sigma y's will be the length of the side of your volume divided by 4.3, regardless of any other information about that volume. But if your source is on the surface, or if it's elevated, or if it's next to a building, your sigma z varies a little bit depending on the configuration of your building. This table again is from the SCREEN3 user's guide. I have a link down here at the bottom that will show you where that is. And actually there's a couple of links throughout this presentation. I just wanted to note, Chandler mentioned that we're going to have this available for review in a couple of days. So if you don't write down everything that you're interested in, don't worry about it. It will be available for playback later. Okay, so we've gone through all of the different source types and the source parameters that we'll need to put into SCREEN3. Another thing we need to decide before running the model is if our if our site is rural or urban. Okay, so the urban option is meant to account for additional turbulence due to the urban heat island effect. Heat islands are urbanized areas that experience higher temperatures than outlying areas. Structures such as buildings, roads, and other infrastructure absorb and re-emit the sun's heat more than natural landscapes such as forests and water bodies. So areas that are urban or industrial or commercial and have lots of concrete, those areas will retain heat, and that'll change the characteristics of the atmosphere in that area. And that's what that urban-rural option is meant to take into account. So the question is, how do you know if your area is rural or urban? Technically, you are supposed to do something called an AUER land use analysis. If you want to do an AUER land use analysis, you basically take a map of your area and look at an area 3 kilometers in radius all the way around your site, and then you break up the land use within that circle into a bunch of different categories. There's industrial categories, commercial categories, residential categories, and agricultural categories. And each one of these categories is assigned to be either urban or rural. And so you take the areas of all of the urban categories and add them together, and the areas of all the rural categories and add them together, and see which one is greater. Whichever one is more than 50%, that's what you end up selecting for your urban or rural selection. And I'll tell you personally that 9 times out of 10, my selection is rural, even in a place that seems like it could be urban. I've done projects in the Houston Chip Channel where it's just, chemical plant after chemical plant, but because the source itself might be on the water, when you draw this 3 kilometer radius, a lot of the stuff inside your 3 kilometers is actually water, and that's considered rural. So just keep that in mind. Meteorology. A huge benefit about running SCREEN3 is that you do not have to process or collect any extra meteorological data. SCREEN3 runs through a set of screening meteorological conditions, and it is not able to run site-specific meteorological data. SCREEN3 assumes that a single set of MET conditions persists for a whole hour, just 1 hour, which lets the model predict a concentration averaged over a 1 hour period. Now, there are a couple of MET selections that you can make within SCREEN3. The first one is to select what they call full meteorology, which lets SCREEN3 run through its entire catalog of meteorological conditions, and then it'll pick the one that gives the worst case concentration, and that's the one it'll report to you. And for any kind of regulatory purposes, that's generally what we're looking for. But you do have the option to tell Screen, I'm only interested in a specific stability class or a specific combination of stability and wind speed, if you were interested in specific MET conditions. Stability, just wanted to throw that out there because it's kind of an important MET parameter used by SCREEN3. It's the tendency of the atmosphere to resist or enhance vertical motion or turbulence. So if you have an atmosphere that's very unstable, that would be labeled in SCREEN3 as something low, like stability class 1 or 2, and then a stable atmosphere would be higher stability class 5 or 6. So in addition to the MET selections, the next thing we have to pick is the terrain type. So we have to look at our site and the area around our site and decide if the terrain falls into which category the terrain falls into. Is it essentially flat? Is there simple terrain? Simple terrain means that there's hills or other kind of terrain features that exist within the domain that are higher than the base of the stack, but lower than the top of the stack. That's considered simple terrain. Or if we have bigger terrain features, bigger hills or mountains or whatever that actually exceed the top of the stack height, that's considered complex terrain. So we'll have to pick one of these options for SCREEN3. So then SCREEN3 will only calculate concentrations at the locations you tell it to use. And it'll calculate a concentration anywhere you put a receptor. Receptors in the model can be put as close as 1 meter to the source and as far away as 50 kilometers from the source. And anywhere along that line, you can add discrete receptors. One place you might want to add a receptor is at the nearest fence line location from your source. That's frequently a regulatory driver wanting to know what that fence line concentration is. If, say, you have a neighbor that is reporting odor complaints or something, and you're concerned about how some change in emissions might affect that person specifically, you can put a receptor at that location and figure out what the impacts are going to be at that particular location. All of these little dots, all of these little receptors in my little diagram are all on the ground, even the simple elevated receptor and the complex elevated receptor. The only difference here is this one in the middle that I've labeled flagpole receptor. So most regulatory modeling specifies a ground level concentration on the ground. If this is not the case, if you're interested in something above the ground, you can select a flagpole height for your receptors, and SCREEN3 will give you that concentration as well. So in addition to those discrete receptors, SCREEN3 will also create an automated distance array of receptors. It'll do both. You don't have to pick one or the other. But the automated distance array is really nice for plots, so you can see how the concentration falls off with distance from the source. Building downwash. Okay, so if you're modeling a point source, and this point source is on, adjacent, or nearby a solid structure, it may be affected by building downwash. So if you look at this diagram, you can see that as air passes over a building, the airflow character is changed. The flow that goes kind of directly over the building is kind of trapped by these little eddy currents on the backside of the building. Some of the airflow escapes the cavity region, but it has some added turbulence in it, and we call that area the wake region. And then some other parts of the flow escape the downwash zone altogether, and we'll just call that the undisturbed region. So SCREEN3 knows about this, and if you turn on building downwash, it attempts to account for changes in concentration due to the building itself. Now, you'll know if you need to turn on building downwash if you have a building that is nearby your source. And nearby, the word nearby really means it's within 5 L of the downwash structure, where L is the lesser of the building height or the projected building width. Most of the time that L ends up being the building height. So if you have a building that is 50 feet tall, then your source has to be within 250 feet of that building. Otherwise, it's too far away to be affected by building downwash. What is a downwash structure? What qualifies as a downwash structure? There aren't any regulatory, at least there's no EPA guidance that I'm aware of that tells you what is and what is not a downwash structure. So this is just a little more of a rule of thumb than an actual rule. But downwash structures are anything that is solid, mostly enclosed, and sit on the ground. And the idea is that they are changing the flow of air around that structure. So things like this really large tank or a solid building over here on the left, these are definitely downwash structures. But if you have like a horizontal tank that's elevated above the ground, the air can flow underneath it as well as above. I would not include that as a downwash structure. These are some process vessels also elevated. I would not include these as downwash structures. Anything, I think these are loading arms for marine loading. It's mostly piping and equipment, not downwash structures. Pipe racks, not downwash structures. This looks like a little storage area that has like an awning over it and maybe one wall on the back. It's not a solid structure, not a downwash structure, and the water tower as well. But it's not always obvious if something is a downwash structure and if it isn't. And obviously the best way to get an answer for this is to ask your regulatory agency. Quick note, do not include the stack itself as a downwash structure. Now, stack tape downwash is an actual thing, and it's already included within SCREEN3. You don't need to add the stack itself as a downwash structure. Last note about downwash. Of course, they're mowing my lawn during the webinar, just so you know what that sound is. Okay, so downwash is the devil. And all I'm saying is that when you turn on downwash, sometimes your concentrations go up dramatically from what they were without the downwash. So it's not optional. You're required to use building downwash, at least for regulatory applications. So be sure you understand what that is before running the model. Okay, there are a few other bits of input data that have to go into SCREEN3 that are just considered regulatory defaults. I would not change any of these unless you are intentionally wanting to turn on some of the non-regulatory options. This is just these are just set by SCREEN3. The ambient temperature in SCREEN3 is 293.15 Kelvin, which is 68 degrees Fahrenheit. The mixing heights are set at a regulatory default algorithm. The anemometer height is set at 10 meters, and the cavity calculation is set at a regulatory default. There's also an option to turn on an inversion or a fumigation calculation, which can be interesting if you have a source that is like right on the shoreline. But in general, you don't want to turn those on unless you've been asked to turn them on and do a fumigation calculation. Okay, so those are the inputs. I think we said the inputs are the vast majority of what you have to do with SCREEN3. Briefly, the outputs. Okay, so SCREEN3 will calculate a 1 hour concentration. Because SCREEN3 uses screening meteorology, it can only predict a concentration over a 1 hour period. So this is a table that comes out of the SCREEN3 for Windows program. After you've run SCREEN3, it tells you what calculation procedure it uses to do its estimate. It'll tell you the distance from the source to the maximum impacting receptor, and it will tell you what that concentration is. The one in the green box is the actual only value that comes out of SCREEN3 for our worst case concentration. But if we're interested in, say, an SO2 3-hour average, we'd need to use a 3-hour number. If we're looking at PM 2.5 24-hour, we'd need to use a 24-hour concentration. And in order to calculate those other averaging periods, we just take the 1 hour value that's collected by a SCREEN3 and multiply it times a scalar that's set in the SCREEN3 manual. You'll get a plot like this that comes out of SCREEN3 for Windows if you've turned on the automated distance array that shows what the concentrations are. This is really close to the source. And then as you get further away, you'll see the concentrations drop off with distance. So the last thing I want to do here is go through a few examples where we actually run SCREEN3 all the way through. And so I'm going to alternate a little bit here between the presentation in PowerPoint and the SCREEN3 itself. Okay, so this is our example number 1, and it is for a gas field flare. So in this case, gas sent to a flare in an oil field is more sour than originally anticipated. The SO2 permit limit needs to be increased by an additional 17 pounds an hour in order to accommodate the gas. Question: will the increase in SO2 emissions cause an exceedance of the 1 hour SO2 cell of 7.8 micrograms per cubic meter? What we know about the flare is that it's 55 feet tall. We know on average the gas sent to the flare has a heat content of 1,050 BTU per scuff and a flow rate of 0.25 million scuff per hour, which equates to a heat release of 262,500,000 BTU per hour. This flare is on a tiny little postage stamp sized property, and so the flare is actually only 10 feet from the nearest property line. And we're going to assume that there are no nearby structures, the area is rural, flat terrain, and all other defaults. So I'm going to go ahead and just put the PowerPoint here in the background, and I'm going to run SCREEN3 for Windows. So on SCREEN3 for Windows, we have 3 tabs here with all of our input data that we have to fill out. On the first one, we're just going to put in a title. I'm just going to call this gas field flare. And it's a flare, so the source type I'm going to change here from point to flare. Our terrain options, we're going to keep this at flat terrain. I'm not going to do a fumigation calculation here because it's not a shoreline source. We're keeping the rural urban option here on rural. For meteorology, we're going to keep this on our full meteorology option. This lets SCREEN3 run through all of the meteorological conditions. We're going to keep the default anemometer height here at 10 meters, and we're going to keep the regulatory mixing height option. All right, so we'll go to the next tab, which is the source information. So we need the emission rate, the stack height, and the heat release. Let's see, our emission rate of SO2 is 17 pounds an hour. The stack height, I think it was, yeah, it's 55 feet tall. And the heat release is 262,500,000 BTU per hour. Okay, there's no structures anywhere around here, so we don't need to fill in any of the building information. We want to leave this regulatory selection alone. And so we're done with the source tab, and we'll go on to the next tab, the receptor tab. So where do we want to put in our receptors? I think putting in this auto distance array is a good idea. Then we can see where all of our concentrations are over time or over a distance. We do know that the flare is 10 feet from the nearest property line. So I'm definitely not interested in anything less than 10 feet. So I'm just going to change this minimum distance here. It says 1 meter. I'm going to change the meters to feet and then change this to 10 feet. So it's going to start calculating our concentrations at a minimum distance of 10 feet from the source. Okay, so that's all of the input data. We have everything we need in SCREEN3. I'm going to hit the save button just so I don't lose this. And this is going to be the gas flare. Okay, so now I'm totally ready to run SCREEN3. So I'm going to click on this button right here with a little lightning bolt on it, and that is going to run SCREEN3. And oh, okay, I got a little pop-up that says, where do you want to put the output file? And I'll just say, sure, that's fine right there. All right, and before we run, we get this little pop-up diagnostic screen, and it looks for any potential warnings or errors. And if anything kind of tipped off SCREEN3 that the model wasn't going to run, it would put a note over here on the right side. But luckily, we don't have any warnings or any errors, so it looks like it's going to run okay. We're going to go ahead and click run. And you might have heard a little beep from my computer. That was it. And so now we can look at the outputs. We can look at a plot, and we can look at the text. The plot looks kind of like this. We did choose the automated distance array, so it's got receptors all the way out to 50 kilometers. So we can see the concentrations are pretty low, really close to the flare, and then they peak up right around here, and then they drop off as you go out with distance. And so let's look at the text here. In the text, we can see that well, it takes a long time, over a kilometer from the site to hit our maximum concentration. And then these are the concentrations predicted by the model. Okay, so what are we looking for here? It says, will the increase in SO2 emissions cause an exceedance of the 1 hour SO2 SIL of 7.8? So the 1 hour number is right here. It's 2.19. That is less than 7.8. So lucky us, this gas field flare SO2 impact is below our SIL. So we are pretty happy about that. I'm going to go ahead and go on to the next example. Example number 2 I have is for a new cooling tower. So we're going to say a new cooling tower needs to be built 200 feet from the property line. Question, will the PM2.5 concentrations generated by the new tower exceed the 24-hour average PM2.5 SIL of 1.2 micrograms per cubic meter? The cooling tower will emit PM2.5 at a rate of 0.05 pounds per hour. The tower itself is a downwash structure, and it has a length of 100 feet, width of 25 feet, and the height of 30 feet. The total airflow the cooling tower, or through the cooling tower, is 300,000 ACFM at a temperature of 95 degrees Fahrenheit. Now, there are 4 cooling tower cells flush with the top of the tower. If we weren't using SCREEN3, if we were using a different model, we might put a different source in for each of these cooling tower cells. But we can't do that. SCREEN3 only lets you model one source. So what we're going to do is kind of merge these 4 cooling tower cells into one gigantic cooling tower cell that will be effective for the entire cooling tower. So in this case, the total area of the top of the cells is almost 2,000 square feet. And if I back out an effective diameter, I end up with a 50-foot diameter for this effective cooling tower. And we're going to assume rural dispersion, flat terrain, and all other defaults. Okay, so I'll open SCREEN3 again. And this time we're modeling a cooling tower. This one we're going to model as a point source. We know that it's got an elevated temperature. We know that it's got some velocity to it. And we have that information, so point source is probably our best representation here. We're going to keep flat terrain on. I'm going to turn off fumigation. Again, we're not a shoreline source. Keep this on rural dispersion here. I'm going to keep our meteorology on full meteorology, let SCREEN3 run through all the MET conditions, keep our default ambient temperature, and keep our default anemometer height and the default mixing height algorithm. Okay, next tab is where we put in all of our source information. Emission rate, 0.05 pounds an hour. So very small emission rate there. Stack height, we know that the cooling tower cells are flush with the top of the tower, and the tower has a height of 30 feet. So we're going to use a 30-foot stack height. Stack diameter, that's our big effective 50-foot stack diameter. Now, I didn't see an exit velocity here in the description, but I do see a flow rate, 300,000 ACFM. So we can put that in there, and it'll automatically populate the exit velocity. And we do have an exit temperature here of 95 degrees Fahrenheit. We also know that the cooling tower itself is a building. It is a downwash structure, so we'll need to put that in as well. The height of the cooling tower is 30 feet. The length is 100 feet. The width is 25 feet. Okay. So we're done with the source tab. I'm going to go ahead and move on to the receptor tab. And we're going to use the same approach as we did in the last example, as we only want to model receptors that are outside the property line. So we know that the cooling tower needs to be built 200 feet from the property line. So I'm going to change this minimum distance to 200 feet. Sorry. I'm going to save my file. So I just typed a whole bunch of stuff in there. Okay, so I have all the inputs ready in SCREEN3, and I'm ready to run. So I'm going to click the lightning bolt to run SCREEN3. Yes, I'm fine saving the output file right there. Here's our diagnostic screen. Luckily, no warnings, no errors, so we're ready to go ahead and hit run. Boom, okay, that's SCREEN3. Now we can look at the outputs, at least from our graph. We can see, again, really high impacts very close to the cooling tower, and then it drops off really dramatically after that. So now I'm going to look at the text. This looks a little bit different than the last time. We have our calculations here with our simple terrain algorithm. And then we also have some cavity calculations. These are concentrations inside the cavity behind the building. I do want to note here this distance from the source to the nearest receptor. Our highest concentration using this algorithm is at 200 feet, which is at the fence line. But the concentrations within the cavity, and these two cavity calculations, are all inside the fence. They're less than 200 feet. So luckily, we should be able to ignore the concentrations from both of the cavity calculations, since those are inside our fence line. So what question are we trying to answer here? Okay, Will the PM 2.5 concentrations generated by the new tower exceed the 24-hour average PM 2.5 cell of 1.2? So we're not looking for a 1-hour average here. We're looking for a 24-hour average. And the 24-hour average number is 0.96 micrograms, which luckily is less than our PM 2.5 cell of 1.2. So yay again, that's another one that passes. That's pretty lucky. And then I do have one more example to show you guys. And this one's for a landfill leachate pond. So we're going to say a leachate pond at a municipal landfill emits hydrogen sulfide at a rate of 1.7 pounds an hour. The question is, do the H2S concentrations generated by the pond exceed the 1-hour Texas state property line standard of 108 micrograms per cubic meter? Now, this pond is approximately 300 feet wide by 1,000 feet long, and there's a buffer zone of 1,250 feet between the pond and the nearest property line. We're going to assume, again, we're in a rural area, flat terrain, all other defaults. Okay, so back to screen 3. This one, Leachate pond. And this is an area source. It's a fugitive area. So we're going to change the source type. We're going to keep it in flat terrain, keep the rural option, keep full meteorology. We're going to let it look at all wind directions. We're going to keep the regulatory mixing height option and keep the regulatory anemometer height. So I'm going to go on to the second tab here, which is the source information. Emission rates, 1.7 pounds an hour of H2S. The release height, well, it's a pond, and that pond is ground level, so I'm going to put a release height of 0. And then we need the longer side length and the shorter side length. That's what it was. 300 feet wide by 1,000 feet long. So the long side is 1,000 feet. The short side is 300 feet. And that's all I can fill out on this tab. The last one is our receptor tab. And we're wondering, how close are we to the fence line? This says there's a buffer zone of 1,250 feet between the pond and the property line. So I'm going to change this minimum distance to 1,250 feet. I think I have everything in the model for the inputs, so I'll hit save and call this Leachate pond. So now I'm ready to go ahead and run screen 3. I'm going to click the lightning bolt to run screen 3, save the output file on the desktop. And luckily there are no errors in my diagnostic screen, so I'll go ahead and hit run. Okay. Screen 3 is finished. We can go ahead and look at the outputs here in the plot. And this is a nice, really smooth plot of concentrations with distance from the pond. I'm going to take a look here at the text. Okay, so the distance to the maximum here, oh, that's our buffer zone, 1,250. So our worst case impact happens right at the fence line, which I guess isn't all that surprising. So the question we're trying to answer here is, do the H2S concentrations generated by the pond exceed the 1-hour state property line standard of 108? The 1-hour concentration, oh, yep, 286 micrograms. That definitely exceeds the standard of 108. So unfortunately, it's back to the drawing board for everyone to make sure we have the best emission rates available and the right characterization so that we can get whatever we want to do approved. And that, I think, is everything here. I just want to say thank you to everyone for joining us for the webinar. I know we went through a whole lot of information in a really short amount of time. Definitely feel free to ask questions through the chat features in here, or you can email me or call me later to ask whatever you like.
Yeah, thanks, Leslie. So if anyone has any questions, please just use that question and answer box at the bottom of the screen. Then again, this session is recorded. I see, Leslie, you have some questions that we're going to try to get to. Do you see them in that open box?
Yes. So I have a question. Let's see. From John, is there any influence on length to width ratio of an area source, or is there a difference between a square and a rectangle of the same area? So there is, if you look at specific wind directions, let me actually bring up the screen for you real quick. I can stop this. Okay. If you are in SCREEN3 and you pick an area source, you have this option over here to pick all wind directions or a single wind direction. If you have a source that's a square that's like, or I'm sorry, a rectangle that's like longer than it is wide, you're going to get different impacts depending on what wind direction you look at. Other than that, I'm not aware of any other differences. Okay, so I have a question. I have a question from Kim asking, can you go through an example of receptor setup for simple elevated and complex terrain? I will go ahead and show you that quickly. If you have a, let me go ahead and open one of the ones that I've done already. So this is our gas flare example. And then this one we had a flat terrain, but let's say we had a simple elevated terrain. You check that simple elevated terrain box. And then what happens is in our receptor box, we have some more options. And what we do is if we want to do an auto distance, like say that we have a hill that starts, 100 feet from our source and ends at 150 feet from our source, and that hill is 15 meters tall. We put that in there as this automated distance. And then let's say after we get beyond, after we get beyond 150 meters, we can say, well, after we get past 150, we can say 150 to 300 meters, that area has a height of only 5 meters. And we can go through as many elevated auto distances as we like. Or if you're concerned just specifically about peaks, that's probably a reasonable thing to do. You just say, I have a peak somewhere, at exactly 423 meters away from the source, and its height is 50 feet or something. The only thing is this height has to be less than the height of the stack. And I'm not sure that it is for whatever example it is we're using. If we go back and use the complex terrain, then we have the option to put in the complex discrete heights over here. So anything that's above your stack height, you can put up in this box. I got a question from Tammy. She says, does the type of contaminant enter the model? And the answer is no. The model will treat every type of pollutant exactly the same, whether it's particulate or hydrogen sulfide or mercury or whatever. It's all treated as a non-compressible or non-buoyant gas. Yeah, I think that's it.
Okay, guys, we'll leave the question and answers open for a few more minutes in case you have any questions or anything you want to ask Leslie. All right, everyone, and as a reminder, this session was recorded. We're going to upload it to our website under the Resources tab, and we can also email it to you. We'll use the email that you registered for the webinar for. All right, guys, we don't see any other questions. So thank you again for attending our webinar, and thank you to Leslie for sharing her expertise on SCREEN3. If you have any other questions, you can email us at marketing@providenceeng.com, or Leslie had her email up at the end of the webinar that you can also email her. All right, we're going to go ahead and end the webinar. Thanks again for attending.